and welcome to the Screencast, where we will introduce the fundamental trigonometric identity. An identity is an equation that is true for all possible values of x for which the involved quantities are defined. For example, the quantity x plus 3 divided by 5 equals x divided by 5 plus 3 divided by 5 is an identity because this equation is true for every value of x, and the left and right sides of the equation are simply two different looking but completely equivalent expressions. Trigonometric identities are simply identities that involve trigonometric functions. While there are a large number of such identities that we could study, we choose to focus on the most important trigonometric identity, the fundamental trigonometric identity. The fundamental trigonometric identity states that for any real number theta, sine squared of theta plus cosine squared of theta equals 1. It turns out this is really just a restatement of the Pythagorean theorem. For example, given an angle theta in the unit circle, we can draw a corresponding right triangle, and we know that the adjacent leg is cosine of theta and the opposite leg sine of theta. And by the Pythagorean theorem, sine squared plus cosine squared would equal 1 squared. Identities are important because they enable us to view the same idea from multiple perspectives. For example, the fundamental trigonometric identity allows us to think of cosine squared of theta plus sine squared of theta equals 1, or if we isolate cosine squared of theta, then we have the cosine squared of theta equals 1 minus the sine squared of theta. Alternatively, isolating sine squared of theta results in the sine squared of theta equals 1 minus cosine squared of theta. There are two other related Pythagorean identities that involve tangent, secant, cotangent, and cosecant, which we can derive from the fundamental trigonometric identity. So if we start with the fundamental trigonometric identity, sine squared of theta plus cosine squared of theta equals 1, and divide both sides by the cosine squared of theta, we see that we would have sine squared of theta divided by cosine squared of theta plus cosine squared of theta divided by cosine squared of theta, and that would equal 1 divided by the cosine squared of theta. We know that the tangent of theta is sine of theta divided by cosine of theta, and we know that the secant of theta is 1 divided by the cosine of theta. Using those facts, this equation actually simplifies to tangent squared of theta plus 1 equals secant squared of theta. And just as we did with the fundamental trigonometric identity, we could rearrange this identity and view it as 1 equals secant squared of theta minus tangent squared of theta, or tangent squared of theta equals secant squared of theta minus 1. A similar argument can be made if we start with the fundamental trigonometric identity, sine squared of theta plus cosine squared of theta equals 1, and divide both sides by sine squared of theta. The result would be 1 plus the cotangent squared of theta equals the cosecant squared of theta. And this identity, like all trigonometric identities, is true for every value of theta for which the involved quantities are defined. These identities prove useful in calculus when we develop the formulas for the derivatives of the tangent and cotangent functions.